Hello to everyone, and thanks for coming to the talk and for inviting me and Ingrid to give this talk. So today we're going to talk about a very massive galaxy cluster, which is named El Gordo, and how its high mass and high inflow velocity, together with its high redshift, pose a significant problem to the ΛCDM cosmology. So as most of you probably know already, it's commonly accepted that the structure formation in the universe took place in a hierarchical way. This is that smaller structures formed first, and then by the effect of gravity, they came together and merged into larger structures until they gave rise to the larger structures that we can find, which are the galactic clusters. So one would expect that if we got the cosmological model right, these cosmological models should be able to accurately predict the timescale in which these structures formed. So what happened is that in the recent years, the telescopes improved very much their capacity for observing farther and deeper into space. And because of this, we have been able to observe in these recent years, for the very first time, objects which are at very far away distances. And what happened when we found these objects is that we saw that they had masses, or they had inflow velocities like the bullet cluster, that were significantly higher than what one would expect for a ΛCDM cosmology. For instance, in a ΛCDM cosmology, one would expect that at redshift about 1, the maximum mass of an object that we should encounter should be around 1.7 times 10 to the 15 solar masses. And this should be like the maximum mass, and objects this massive should be extremely rare. And then we observed El Gordo, which has 3 times 10 to the 15 solar masses at redshift almost 1. So we're going to talk about this very special object in a bit more detail. So El Gordo is an interacting cluster at redshift 0.87, composed of 2 very massive subclusters, which have a mass ratio of 3.6. This is, this is a major merger. And yeah, they are inflowing into each other at a very high speed. And because of this very high mass of the system and high velocity of the system, the interaction is very energetic. And this makes El Gordo the most X-ray luminous and brightest Sanjeev-Zeldovich galaxy that we observe at this redshift. Another particularity of El Gordo cluster is its X-ray morphology, which is characterized by 1 single peak and 2 fin tails. In this picture, you might actually see better this morphology of 2 tails. So this particular feature of El Gordo can also be seen as a dip in the X-ray emission of one of the clusters caused by the passage of the other cluster. Therefore, what this dip is telling us is how the interaction of the 2 subclusters took place, which is going to be very relevant if we want to understand how El Gordo came to be. So we know that El Gordo is an extremely rare cluster in ΛCDM cosmology, but we want to quantify exactly how rare this cluster is. And to do so, we follow the method described in here. So for starters, we know how the primordial density fluctuations look like from the CMB. And if we want to know how these primordial density fluctuations evolved according to a certain cosmological model with time, we use the cosmological n-body simulations. Therefore, like we said before, if this cosmological model is correct, we should be able to find an object like El Gordo in this cosmological simulation at the redshift at which we observe it. There's a tiny problem. There's a problem about this, and this is that for estimating reliably the number of analogs of an object as big and massive and extreme as El Gordo, we would need a very, very large simulation box. And the larger your box, the lower your resolution. Therefore, we can't simply aim to find an object in these simulations that matches, let's say, the very particular X-ray morphology of El Gordo, because we don't have the resolution to do so. What we can actually do is look for cluster pairs whose properties could allow them to potentially form a merger like El Gordo in a posterior time. So if we want to know what these particular properties should be, we should actually make use of the hydrodynamical simulations. The hydrodynamical simulations, what they do is they set up an initial configuration. So they would choose a certain value for the impact parameter, certain values for the masses and mass ratios, and certain values for the initial velocity. And then they would evolve this initial configuration until they would evolve with time until they reach the configuration of interest, which in this case is the observed configuration of El Gordo, which is when its two clusters are separated by about 700 kiloparsecs, more or less. So once we have our picture for the observed configuration, we ask ourselves, well, or the authors ask themselves, does it actually match the high luminosity of El Gordo? Does it have its X-ray morphology? And does this morphology match in the case of X-ray and Sanjeev-Seldovich? So yeah, we basically use the simulations to see if an initial set of parameters can give us the observed features of El Gordo. So there have been many works analyzing these sort of scenarios and trying to constrain the properties of the initial configuration of El Gordo. But out of all these works, we chose the results from Zhang et al. The reason for this is because they performed one of the most recent hydrodynamical simulations of El Gordo, and also they are one of the groups that better managed to reproduce the features of El Gordo with respect to other hydrodynamical simulations. So Zhang et al. Ran 123 simulations, testing different parameters, and they distinguish between two scenarios. On the first scenario, they consider that the collision is extremely energetic and it's head-on between the two clusters. This scenario would require a mass which is not so high, but that would need a very high input velocity. And also the mass ratio should be very small, like they should be almost about the same. I mean, it would be a very major merger in this case. And the problem with this scenario is that it doesn't reproduce the two-tail morphology that, like we said before, it's kind of important. So we consider this model, and they consider this model not to be so good. And so they propose a different scenario. This different scenario would correspond to model B. And in model B, what we would have is that the collision wouldn't be so energetic, it would be kind of off-centered. And this type of scenario would require, in this case, a very high mass, but not such a high inflow velocity. And even if it's still a major merger, it's not as and the mass ratio is not as small as in Model A. Good thing about this scenario is that we can actually match the two-tail morphology, like maybe you can see from the picture. So yeah, from now on, we consider the results from Zhang et al. Model B as the results which we are going to work for our statistical analysis. So that's it for the hydrodynamical simulations. Regarding the cosmological simulations, we chose to use the simulations from the Jubilee project. The Jubilee project made some of the largest simulations that n-body simulations that have ever been done. And for this project, like we said, we need a very, very large simulation box. So we actually use the largest volume box that they have available, which is of 6 times 6 h to the minus 1 co-moving gigaparsecs cube volume box, which is very, very large. So like I said, this is an embodied simulation. It assumes a ΛCDM cosmology, and it's based on the results of the WMAP, which are these ones. Afterwards, the halos were identified using the Amiga halo finder algorithm. And they did this at redshift 0, at redshift 0.509, redshift 1, and redshift 6. And this is going to be very useful in the next slides. So regarding the resolution, and they used a particle mass of 7.49 times 10 to the 10 e to the minus 1 solar masses, and their lowest halo has like 20 particles, so minimum mass should be 20 times this. Like we will see in a moment, the masses of the objects that we're going to use are significantly larger than this, so we shouldn't be worried about problems of resolution in this case. So once we have our very, very big box with our many, many objects, we have to actually classify them into pairs to find those that could be potential progenitors to El Gordo. So first things first, we remove galaxies from our sample, since in this case we're just interested on galaxy clusters, not galaxies. So to do this, we impose a mass limit, and we require all the clusters to have a mass of 3.5 times 10 to the 13 solar masses. And once we have removed galaxies, what we do is compare the pairs with each other. Since we have so many pairs, this would actually take a lot of time. So we simplify things by using a tree-based code. What this tree-based code does is it only compares clusters which could have possibly had an encounter within 100 times the lifetime of the universe, which is very conservative, but it still saves us a lot of time. So, okay. Once we have compared our pairs, we select those which have turned around from cosmic expansion. This means that they could plausibly they could possibly be falling into each other at some point, which is kind of necessary for having a merger, and that they have a mass ratio smaller or equal than 3.6, which is the mass ratio estimated by Zhang et al. In its hydrodynamical simulations. So in order to be El Gordo analogs, these cluster pairs we actually need to match further conditions. For example, we require them to be at redshift 1 because we are looking at El Gordo progenitors, so we need to go to a redshift which is slightly higher than that at which we observe El Gordo today. And regarding the values for the parameters that will determine the initial configuration, we require them to be equal or more extreme than the values estimated by Zhang et al. In their simulations. In this case, we also remove the dependency of these parameters with any other properties that the cluster pair should have by scaling them over these properties or parameters. And this is where our tilde notation comes from. In the case of the total mass, what this tilde notation is telling us is that we're working in log scale and in units of solar masses. So what happens when we try to impose all these conditions to our selected pairs is that the moment we impose the mass condition, we just run out of analogs because there is no cluster pair in the entire, there's no cluster pair among our selected pairs that has a mass that is as large as the mass of El Gordo. So in here, we could think that we run in a bit of a problem because how do we estimate the number of analogs in a simulation box in which the number of analogs is 0? So what we do to fix this is we plot the cumulative distribution function in terms of the m tilde that we define here, and in terms of the number of objects that have a mass above a certain m tilde. And what we do is we apply a quadratic fit to this cumulative distribution function, and we extend this quadratic fit until we reach the point corresponding to El Gordo mass. And it's from this fit that we infer what would be the number of analogs of El Gordo at this mass, which would be something smaller, smaller than 1, 0.10 to the minus. Yeah, that's what I meant. Yes, so we actually do this for several constraints, from more relaxed constraints, in which we simply require the clusters to be infalling with some velocity, to more realistic and also strict constraints in which we require the clusters to have a velocity at least equal or higher than that of El Gordo, and an impact parameter smaller or equal to that of El Gordo. Also, like you can see in this plot, the results that we obtain from asking for the V tilde condition alone and asking for the V tilde condition together with the impact parameter condition are very similar. I mean, we get almost same results. So from now on, to be more conservative and also for simplicity, we consider as our nominal results those given by the constraint of V tilde alone. So, okay, from this graph, you can already have an idea of what would be the number of El Gordo analogs for this condition, which should be something around 10 over minus 7.5, which is actually 3.16 times 10 to the minus 8, which is very, very small. And yeah, this would be the number of analogs for the entire Jubilee simulation box of 6 h to the minus 1 comoving gigaparsecs. We should take into account that the survey in which El Gordo was found was significantly smaller than this volume. And so to give an accurate result for the number of analogs that we should expect to observe, we should scale the volume to that. So we ask ourselves, how many analogs does this correspond to in the El Gordo survey volume? To answer this question, we would need to know what was El Gordo survey volume. So on the one hand, we already know the survey area, which is just given in the paper describing its properties. And on the other hand, we would also need the survey depth. So the way we constrain the survey depth is by taking into account that the number of El Gordo analogs will decrease very rapidly, and therefore this effective depth is going to be very, very, very small. And because we know that the survey depth is going to be very small, we can actually consider that the number of analogs is going to be about constant in a certain redshift interval, and it's going to drop to 0 after that. Yeah, this is what we kind of show in this picture. The only difference is that instead of talking of redshifts, we're talking of a scale factor A, which is related to the redshift in this way, but yeah, it should be the same. So in this region, the number of analogs should be about constant because this delta E is going to be very, very small. And we consider that beyond this, the number of analogs drops to 0. So in order to know the survey depth, we're going to need to know what this delta A is, and it's what we're going to find out in a moment. So how do we obtain delta A? To obtain delta A, the first thing we do is expressing the number density of analogs in terms of the scale factor. Like we said before, the number of analogs is going to decrease very rapidly with increasing redshift, or what its equivalent is going to increase very rapidly with the scale factor. So because of this, we assume that the relation is that of a power law, and we assume therefore that the number of analogs is proportional to the scale factor to the power of k, where this k is the growth index, which is obtained by estimating the number of El Gordo analogs at redshift 1 and at redshift 0.509, and seeing how it increases with the scale factor A. So this formula over here. So now that we know how to express the number density of analogs in terms of the scale factor A, we can go to calculate the number of analogs in the observed moving volume at a scale factor which is equal or smaller than that at which we would expect to observe El Gordo progenitors. So yeah, to do this, we do something very intuitive. We integrate the number density of analogs over the co-moving volume. And then we just do a variable change in order to have this expressed as the differential of the scale factor. And then we just express everything as a function of the scale factor. So we have a very simple integral that we know how to solve. And we get this result over here. Like we said before, because we know that this volume is going to be very, very small, we can assume that this approximation holds. This is that the number of analogs is going to remain constant in a certain volume, and then it's just going to drop to 0. So we can actually say that the result from doing this is going to be equivalent to the result of doing this thing above. So we just equate this result with this result, and we obtain our delta A, which in the case of our nominal result, which is that which has the utility constraint, is of 0.015, which, like I said, is very, very small. So now that we have what this redshift or scale factor interval is, we can go and calculate the effective volume. So the effective volume is defined as the area of the survey, times the co-moving distance squared. This would be the distance to the scale factor at which we expect to observe El Gordo analogs, or the analogs to El Gordo progenitors. And also this should be multiplied by the delta D co-moving, which should be the distance corresponding to this redshift or scale factor interval that we calculated before. So from this, we can actually get our effective volume. And from knowing our effective volume, we just need to calculate the expected number of Gordo analogs in the survey, which is very small, again. So if we want to be a bit more accurate and express this as a probability, and also as the number of standard deviations, what we do is we use the Poisson equation, in which we just plug in the n survey that we obtained. And well, we obtain a very similar result because this number is very small. And then if we want to obtain the number of standard deviations from this, we would just apply the Gaussian equation and we would solve for chi. And this would leave us with a chi value of 6.7 sigma, which is significantly above the 5 sigma falsification threshold. So this is what we obtain with one method, since we wanted to make sure that our methods are reliable and consistent and make sense. We actually try to obtain the number of analogs in the Gordo survey volume, once again following a different method. And this other method, it's called the Litecoin tomography method, and it consists on constructing a grid for different m tilde and scale factor values and obtaining the number of analogs from that grid. The way we do this is, once again, we remember that we could fit the cumulative distribution function with a quadratic equation. And therefore, with this equation, we could know what was the number of objects that had a higher mass than certain m tilde for any value of this m tilde. So now if we also want to know what's the dependency of this number of objects with the scale factor A, because that's what we would need to construct this grid, what we do is we try to obtain this equation by repeating the fit at redshift 0, at redshift 0.509, and at redshift 1. By doing this 3 times, what we obtain is 3 different values for each of these coefficients corresponding to each redshift. And then we use a quadratic fit in log scale to actually fit the values of the coefficients in terms of the scale factor. So we can infer what would be the value of these coefficients for any scale factor value. So in this way, we have actually managed to obtain the number of analogs for any m tilde and any scale factor A, which is what we wanted. Besides this, once again, we account for the fact that this number of analogs is the number of analogs for the entire tubular volume, but what we're interested in is the volume of Gordo survey. So we just scale this number of analogs by survey volume in each of these pixels that will depend on the scale factor A. So now we have our grid constructed for several values of m tilde and several factors and several values of the scale factor, and we just go and look at the point that would correspond to the m tilde of El Gordo and the scale factor of El Gordo progenitors. And we find that this corresponds to a 6.16 sigma tension, which is slightly below than the tension that we obtained with the previous method, but is still way above the 5 sigma falsification threshold. So things don't look very well for LCDM, but they can look even worse if we actually take into account that El Gordo is not the only problematic object in the sky for LCDM. So many of you might have also heard of the bullet cluster. The bullet cluster is an interacting cluster which is at redshift 0.3, and it's composed of two subclusters which are colliding with a very high speed, 3,000 kilometers per second. And well, this very high speed is actually needed to reproduce this morphology that we see in this picture. And while we didn't personally quantify how unlikely this object is for LCDM, Kraljic and Sarkar did that for us, and they obtained that the probability of observing the bullet cluster in the whole sky is of 10%. Once again, the survey volume in which the bullet cluster was found was not the whole sky, was significantly smaller than this. And so, accounting for this, we find that the actual probability of observing the bullet cluster in the survey region in which it was found, it's of 5.4 times 10 to the minus 3, which makes it a 2.78 sigma outlier. Now, if we combine the probability of finding El Gordo and the probability of finding the bullet cluster in the sky, which is done using these equations here, what we find is that for the Paolo method, the fact that we observe both objects would falsify LCDM to 6.94 sigma, this using the Paolo method. And if we use the Litecoin tomography, we find that the falsification level is of 6.43 sigma. So, yeah, this is bad. Yeah, as you might see from this table, the results from our Paolo method and the results from our Litecoin tomography method are quite consistent between each other. They just have a difference about 0.5 sigma. This is an error that it's really not going to solve anything. So also what we get from this is that the results from Litecoin tomography are a bit more conservative. So we choose this to be our nominal results to be a bit more conservative. And that both methods agree that LCDM must be ruled out by a significance higher than 5 sigma. We also tried assuming, which is a very generous assumption, that El Gordo and the bullet cluster are the two only problematic objects in the sky. And with this very generous assumption, which is not true, we still would find that the tension is above the falsification threshold in both cases. So even if we didn't find any other problematic objects in the sky, this wouldn't help to solve the tension. What might help solve the tension is if the results from later dynamical simulations were not correct, and we actually had that the inflow velocity of El Gordo is significantly smaller. That would help definitely, because like you can see in this part of the graph, this would reduce the tension below the 5 sigma falsification threshold. But before assuming that we can choose this scenario, we have to make sure that this is actually physically consistent and it makes some sort of sense. So to check this, we go back to Zhang et al. Models. Yeah, so like you might remember from the previous slides, the result they obtained for the inflow velocity of 2,500 kilometers per second, which is the nominal result, actually managed to reproduce quite nicely the two-tailed morphology. But what happens if we reduce this velocity to, let's say, 1,500 kilometers per second? What happens is that the two-tailed morphology is almost gone. I mean, you can still kind of see it, but it's on the verge of disappearing. So we consider that the infall velocity of 1,500 kilometers per second is the lowest plausible collision velocity that El Gordo could have. So now we say, okay, assuming that this is possible, that it could be that El Gordo could have an infall velocity of about 1,500 kilometers per second, would this actually help solve the tension? So we actually repeated our analysis using the Litecoin tomography method, since it was more conservative. And we calculated the chi values, the chi values that we would obtain for different infall velocities. So for the minimum plausible infall velocity of 1,500 kilometers per second, we see that this is actually very slightly below the 5 sigma falsification threshold. But the moment we include the bullet cluster, this surpasses the 5 sigma threshold, so it doesn't really help. And yeah, obviously, if we go forward to more realistic infall velocities, so this tension, yeah, it's again really high, so it doesn't really help that much. So yeah, we conclude that no, low velocity couldn't realistically help solve the tension. We also consider the possibility that the inferred mass from the hydrodynamical simulations was wrong, and this mass should be lower. But in our paper, we demonstrated that this is also not possible, because the lower mass would reduce the X-ray flux. And to compensate for this, you would need to assume a higher velocity, and this would cause problems in another way, and it will again be above the 5 sigma falsification threshold, so it doesn't really help. The other reason why assuming a lower mass isn't really useful, or doesn't make much sense, is because the mass was already constrained by weak lensing, and the weak lensing results actually agree with the 3 times 10 to the 15 solar masses results. So we don't have reasons to believe that the mass should be lower than that. Other possible problems that we considered that our analysis might have is that maybe we had too little pairs after we imposed all these conditions, and therefore the Poisson noise would make us have not so reliable results. But we actually checked this, and we say that we have like 15,035 pairs, and that the Poisson noise for all these pairs, it's only of 8.16 times 10 to the minus 3. So this is probably not the case. And yeah, just to finish, we also considered that maybe we should have been fitting a different mass range in the cumulative distribution function. But in our paper, we demonstrated that this didn't affect the results much. So this wouldn't really make any difference. So yeah, since it seems that we can't solve this problem in the ΛCDM framework, we are going to try to see if we can solve them in another framework. But that is something that Indranil is going to explain to you, not me. So yeah, we're going to pause the presentation a little bit and give a little break, and Indranil will continue in a second.
What I'm going to do is discuss briefly how we might resolve the problems faced by ΛCDM with El Gordo using MOND. So just to briefly recap, MOND is motivated by the fact that galaxies rotate much faster than they should do. So what's shown here is the rotation speed of the galaxy versus the distance from its center. And the Newtonian expectation beyond the extent of the visible mass is a Keplerian decline. But the rotation curves, as you probably know, go flat. So this huge discrepancy is conventionally attributed to cold dark matter halos. Another way of showing this discrepancy is to show the centripetal acceleration from the rotation curve as a function of the gravity that you expect from the baryons using Newtonian dynamics. So this discrepancy here is also shown as this discrepancy here between the line of equality and the actual data points. The idea behind MOND is basically that this relation is fundamental. And this is motivated by the fact that not only this galaxy, but 153 galaxies all follow a very tight radial acceleration relation. Also, the accelerations are very small compared to the solar system. So fundamental modification to the gravity law is possible at such low accelerations. So that's basically MOND in galaxies. But what about cosmology? Before I get onto that, one thing I wanted to mention briefly is MOND doesn't fit every galaxy. Here is an example of a rotation curve which doesn't fit properly in MOND. So this is the MOND fit in the data points. It can be fit quite well with Newtonian gravity and dark matter. But before you dismiss the MOND, you should realize that this galaxy doesn't exist, because the rotation curve corresponds to one galaxy and the photograph corresponds to a different one, which might explain the poor MOND fit. But because you're allowed an arbitrary amount of invisible matter in this panel, it was possible to obtain a good fit. Essentially, what I wanted to say is that anything above the line of equality would be legitimate in ΛCDM, but that's not the case in MOND. Okay, so to keep this brief, I just want to explain how we think MOND works in a cosmological context, which is that the overall mass energy budget of the universe is the same as ΛCDM, except that the cold dark matter component is replaced by some kind of collisionless matter, such as sterile neutrinos with a particular mass. Okay, come on to in a sec. The main purpose of choosing this mass is to have the same overall mass energy budget as ΛCDM. So thermal sterile neutrinos of this mass comprise its 25% piece. You get a standard sort of Friedmann equation. It's a small correction, but it's a very small. Basically, you get a standard background cosmology. So standard primordial element abundances, so it's shown in previous work. MOND matters because the density perturbations in the universe behave differently. Actually, we apply MOND only to the density perturbations. This approximation has been discussed previously. So structure grows faster in MOND, which is going to be important. Now, structure obviously starts growing from very early stages, including before the epoch of recombination. Regarding the CMB, because we have a standard expansion thermal history in the same angular diameter distance, MOND is, however, not very important because the universe was much smaller then. So the gravitational fields are only about 20. The gravitational fields are about 20 A0, suppressing MOND effects. Also, the free streaming of the sterile neutrinos are negligible if the mass is more than 10 eV by c squared, according to the Planck collaboration. The effect on the CMB spectra is identical to CDM. So of course, 11 eV by c squared is legitimate. Much higher mass would also work, but it's not necessary regarding this particular constraint. So that's the CMB, which can be fit very nicely in MOND, as shown with the blue curve versus the ΛCDM fit in red. So there's no reason the CMB should be problematic in MOND. What is important, as we were saying, the structure formation, including the first galaxies that will form faster in MOND. The just to recap briefly, then the new HDM framework with the new sense basically for the sterile neutrinos. You can explain the expansion history, Big Bang nucleosynthesis, cosmic microwave background, also the internal dynamics of galaxy clusters, like the bullet, which Ellen was talking about, because of the assumption of collisionless sterile neutrinos. So same idea as lambda CDM. Galaxy rotation curves are unaffected by the neutrinos, so you just get standard sort of MOND, if you like, in galaxies. And therefore, new HDM solves various problems with lambda CDM on galaxy scales. So in the interest of keeping it brief, I won't discuss these in detail, but you have the satellite plane problem is one of the most serious, but also things like the thin disks, the high prevalence of thin disk galaxies without any bulge, and the fast pattern speeds of bars in galaxies. So I don't want to explain about that now. What I will do is explain what the relevance of this to El Gordo. Now, Katz et al. In 2013 ran a series of cosmological simulations using the new HDM model, because this model has been around since 2009. They found one El Gordo analog. Actually, they ran about 8 simulations. They found about 10 altogether, so approximately one analog per simulation. And this is the simulation volume. So a bit smaller than Jubilee, but despite that, they found one analog. Whereas according to our extrapolation, you get about 10 to the minus 8 analogs in lambda CDM in a box which is about 1,000 times larger. So what does this mean exactly? Well, if we repeat the power law analysis and use the effective survey volume that Elena described earlier, and you sort of scale this number of 1, you get 1.16 analogs expected in the survey volume. What you should understand, the growth index thing that she was mentioning, it might be sort of 30 in lambda CDM, maybe it's only 20 in MOND, but that will only affect this by a factor of 1.5. So it might be 0.7 analogs, maybe 1.2 analog, 1.8 analogs. But clearly the new HDM gets the right order of magnitude, which is completely wrong in lambda CDM. So that's one important thing. The other thing I want to briefly mention is that the lack of such objects, such extreme collisions at low redshift is probably because we're in a large local void called the KBC void, which has been observed in the near infrared. So that's an observational fact. Such a large underdensity is not possible in lambda CDM, but it was predicted a priori in the new HDM model a couple of years before such a large void was discovered. So this is discussed more in the Hasselblad 2020 work, which discusses much more about the new HDM model in a cosmological context, but mainly with regard to how this might solve the Hubble tension. So in the new HDM model, it's possible to solve the KBC void, the Hubble tension, and El Gordo simultaneously with the galaxy scale challenges faced by lambda CDM. Just to get to the conclusions then, the pre-merger configuration of El Gordo was estimated by Zhang et al. 2015, and there are other hydrodynamical simulations. They give very consistent results. And this is why the Katz et al. 2013 work, despite predating it, used basically the correct parameters, which were known for about since 2012-ish. However, these model parameters contradict lambda CDM at more than 5 sigma, very high confidence, regardless of exactly which way you look at the data. Combining it with the Buller cluster, 2.78 sigma tension found previously, scaling for the sky area, get a 6.43 sigma tension. Yeah, you can change the mass and collision velocity, but there's a range beyond which you can't reproduce the morphology of the merger, like what it actually looks like on the sky. So for any plausible mass and collision velocity, including the model A of Zhang et al., which Elena mentioned earlier, we didn't consider as a nominal case, but we did consider it briefly in the paper. And the tension is still more than 5 sigma. Such an extreme collision is, however, quite possible in the new HDM cosmology. It's expected that you would get about 1 in the survey region. This new Asian cosmology, however, was not invented in order to explain El Gordo. It is motivated by Mond's successes in galaxies, and the neutrinos are motivated by the equilibrium dynamics of galaxy clusters, where Mond is known to have a problem if you assume purely baryons. Now, the lack of objects like El Gordo at much lower redshift, which is observed thing, that is probably explained by the near-infrared KBC void. The KBC void, which was discovered in the near-infrared. And that's for the radius of about 300 megaparsecs, out to redshift 0.07-ish, which could also explain the Hubble tension as outflow from the void. So the blog describing our work is available here, and one of the previous posts is about the Hasselblad 2020 work on the KBC void and Hubble tension in Mond. So thank you for listening. I'll be happy to take any questions.